All right, today we're going to talk about work kinetic energy theorem. And now what that is that the net work done by a net force acting on an object is equal to the change of the kinetic energy of that object. So how would we write that out in formula?
Well, we're basically taking the work formula and we're marrying it to the kinetic energy formula. So let's start with what work is. The work formula is what?
Work was force times distance, correct?
Right. Work is equal to force, I can draw a better F than that, times distance. Okay, how about the kinetic energy formula?
Kinetic energy formula was 1/2 times mass times velocity squared.
That's right. Kinetic energy, Ke, is equal to 1/2 mv squared. Okay, but we're not combining the work formula and the kinetic energy formula just by themselves. Okay, we're talking about change in kinetic energy. Work is equal to a change in kinetic energy, which looks like this.
Let me go ahead and stop you right there. You just drew a triangle. What does a triangle mean?
The triangle is Mathanese for change.
Okay, so the triangle equals change.
Yeah. It's just a fun Greek way of saying it.
Awesome. Okay, that's cool then. That way we don't have to actually write out the word change.
Yeah.
You can just do a triangle, okay? So triangle equals change in kinetic energy. All right.
It's just a variable just like anything else.
I didn't mean to interrupt you. Go ahead and continue.
No, it's all right. So, if work is equal to change in kinetic energy, then that means that we're taking the kinetic energy that we end with.
So the final, right?
Yeah, final. And we're subtracting from it the kinetic energy that we started with. So work is equal to change in kinetic energy, which means we have final kinetic energy minus initial kinetic energy.
Okay, that makes a lot more sense then. Okay, so we have, that is going to be for kinetic energy. Now, what if I wanted to find, or what if we didn't have the kinetic energy?
Oh, you mean like if they gave us mass and velocity instead?
Right.
Okay, well there's an easy way to do that. Let's back up a little bit. I'm going to erase this right here. Make sure you got it down. I'm erasing the bottom part. So we know that kinetic energy is equal to 1/2 mv squared. Well, what about final kinetic energy and initial kinetic energy?
Right.
We're still going to use the kinetic energies here, but we're going to sub in the formula for it. So we have work is equal to change in kinetic energy. We're just going to sub in the other variables. We have 1/2 mv final squared minus 1/2 mv initial squared. See, all I've subbed in is the formulas for kinetic energy for those variables here.
Okay, so that makes a lot more sense then. And then we do know that, we remember that mass is measured in kilograms, and we know that velocity is measured in meters per second. Now, the difference between velocity and acceleration is that acceleration would be meters per second squared, and it would be that would be changing.
Hey guys, okay, so we're going to look at some guided practice problems. So if you turn in your packet to guided practice problem number 1, a student wearing frictionless ice skates on a horizontal frozen pond is pushed by a friend with a constant force of 45 newtons. How far must the student be pushed, starting from rest, so that her final kinetic energy is 352 joules? So we are going to use the work energy theorem to apply our concepts. Remember, the work energy theorem, work is equal to force times distance, which is equal to the change in Ke, kinetic energy, which is equal to Ke final minus KE initial, which is equal to 1/2 mv squared final minus 1/2 mv squared initial. Okay, I know this looks really long, and I know this looks really, really confusing, but one of the things I need you guys to realize is that you don't ever use this entire formula. You only want to pick out what is between the equations, what is between the equal signs that you need. So let's start off by writing what we know. We know that our force is equal to 45 newtons. We know that we're looking for a distance. And we know that our final kinetic energy is equal to 352 joules. We know this. So let's use our equation and look at what we have so we can figure out what we need. Right here, we have force times distance. We have a force and we have a distance. So we know we're going to need that. So that's in between two equal signs. Let's find something else in between two equal signs that we're going to be able to use. Well, look right here. We have a KE final and a KE initial. So let's put these together. When we put these together, we're going to be able to see how they're going to work together better. So FD, force times distance, is equal to KE final minus KE initial. Now let's plug in what we know underneath them. Well, first of all, we know our force was 45. We know that we're looking for our distance. We know that our final KE is 352 joules. And we know that she started from rest. So that means we know she started from 0. Rest is always 0. Any object at rest is always 0. You should know that by now. All right, so move forward. What is our next step? 45 times d is equal to 352. The next thing we have to do this is to divide out our 45. So if you divide both sides by 45, it makes it go away. And then when you divide 352 by 45, you end up with an answer of 7.82 meters, because that's our distance. So, I realize this looks really big, long, and complicated, but it's actually pretty easy cheesy if you just pick out the parts you need. And remember, your parts are always between the equations, between the equal signs.